what's the impact of the automation that you're doing, and especially now AI? AI is changing everything, and it's definitely changing EDA.
The chips have just gotten more complex. And there is still a large amount of, I think, human work that's involved. And I would say the core of the original CAD software, like EDA software that we built, it was more built to like deal with very large computational problems, right? Something that actually, to be honest with you, a human isn't really good at.
What impact is agentic and generative AI going to have on chip design and now apparently the design of everything, right?
I have a system that has experience or has learned how to deal with all possible scenarios. Imagine the power that you have on decision making. And it's the same in the chip design world. You essentially bring the power of the expert user into those systems, and they can automate a lot of these things and make this chip design process more automated.
Welcome to Tech Transformed, your go-to podcast for exploring how emerging technologies and AI are reshaping business and society. I'm John Santaferraro, industry analyst at Ferraro Consulting, and your host for this episode. In this session, we'll explore electronic design automation, EDA, the software engineers use to design and test computer chips and complex electronics, and how AI-powered observability is transforming engineering workflows. Joining us today is Dr. Thomas Andersen, Vice President of AI and Silicon Innovation at Synopsys, the undeniable engineering leader in silicon to systems design. Dr. Thomas Andersen. Thomas, welcome to the show.
Hey, John, pleasure to be here.
I'm going to jump right in because there are so many things to talk about what's going on at Synopsys, and especially in the EDA world. So for our audience who may not be familiar with the Synopsys brand, can you take a few minutes to explain what is Synopsys? What do they do? And especially, what is it about Synopsys that makes them important in the AI-driven tech landscape today?
That's a very good question. I fully understand that. I think most of your listeners and most folks probably have never heard about Synopsys, but we provide silicon to software solutions for pretty much all chip makers, whether it's Apple iPhones, whether it's your NVIDIA GPUs, anything that runs in your car, in your smartwatches, in your television. Any chip that's being created is being designed with Synopsys software. So essentially, we are sort of in the heart of your electronic devices, and we create the electronic design automation software that helps design those little chips in there that then run all those devices. So we are a very crucial part and very important in the whole ecosystem chain for semiconductor.
You guys are not new at this game either. You've been around for a while, right? I mean, this is the name Synopsys. At least I grew up in Silicon Valley, so I've heard it for a long time. Can you talk a little bit about your history?
We have been around for a long time. In fact, we were founded in 1986. That makes me sound very old, but I actually wasn't there at the time. So in 1986, I was in high school. So that's how long we've been around. And if you look back at Silicon Valley, I mean, you remember like Intel and Fairchild and the original companies that started in the 70s. They were initially designing their chip circuits by hand. I mean, it's unimaginable to do that today, you know. So there was no software at the time. And in the 80s, somebody, essentially our ex-CEO, Art DeGias, who's the founder of the company, who's still on the board of directors, he's essentially the one who came up with this initial innovation of designing a chip with software rather than by hand.
Since it became electronic and automated, right? EDA, electronic, it must be fairly simple then, right? I mean, you just push a few buttons and you get a chip design. And obviously, I'm joking, but for the audience, you know, what does that process look like? It seems like it's pretty intensive, And I think from what I've heard, it's only getting worse because of what's happening with chip design and what's happening with the world of AI.
That's a very good point. So hardware design, which is what we're talking about here, takes significantly longer than say software design. And I guess back in the 80s, maybe it was easy. I don't know. I wasn't there. You probably pushed a button and you had tiny little circuits and they came out and it was fine. But over the years, the complexity has risen unbelievable. And you have now billions of transistors on a chip. It's unimaginable that anybody would do it by hand. But even with what we call electronic design automation software, which is essentially CAD software that helps you design the chips, there is still a lot of human effort that goes into defining the chip, refining essentially the chip design, lots of tedious manual work. So if let's say you look at some of the big chip companies, you don't have a new chip coming out every month. You have it coming out maybe every year. And that's because these design cycles take so long. So for a company to say, we're going to build the next GPU, it takes them a year or maybe even longer. And it takes hundreds or thousands of people. And it's a huge investment. And by the way, if you go wrong, if you have the wrong specs and you realize after 6 months that your thing is not going to work or it's not competitive anymore, then you pretty much lose a big market share. So it's compared to software, it's much longer and design cycles with a much bigger investment.
Well, I've heard it compared as well to the pharmaceutical industry, where you invest a lot of money in bringing a drug, doing all the research and bringing a drug to market, or same with oil exploration, right? You're out there and you spend a lot of money, and sometimes you don't even know till you use it, right? That it's working. Do you think there are similarities there?
There's similarities there in terms of how long it takes. Luckily, compared to the pharmaceutical industry, you don't have to do human or animal testing or anything like that, but we can do it through software and hardware. But yeah, there is definitely a lot of similarities in how long it takes.
So you've automated a lot of these processes. You've made things a lot simpler. That's cross-industry, right? So what does that mean in terms of the time that it takes to deliver a chip, the amount of human effort that has to go into it? What's the impact of the automation that you're doing? And especially now AI, AI is changing everything, and it's definitely changing EDA. Can you talk about that?
Yeah, definitely. We estimated that over, I think, the last, 35, 40 years, we provided something in the range of 10 to the power of 7, so essentially 7 zeros, level of productivity improvement through EDA software. So that's compared to doing it manually. But at the same time, the chip complexity has risen so much. So essentially every time you make some improvement there, your next chip is 10 times bigger and so much more complex. So therefore, the design cycles really haven't shrunken, right? The chips have just gotten more complex. And there is still a large amount of, I think, human work that's involved. And I would say the core of the original CAD software, like EDA software that we built, it was more built to deal with very large computational problems, right? Something that actually, to be honest with you, a human isn't really good at. Like, let's say, if you ask me to compete with a calculator, I have no chance. A calculator will beat me, and a calculator, you can say, is a relatively not very advanced device. But on something like that, it completely outdoes me. And yet, the human, of course, has cognitive capabilities, reasoning capabilities that even AI, of course, has not reached yet. So there are human aspects of chip design that have not been automated simply because they're not in the computational domain. Maybe they're in the experience, in the reasoning of I've seen this problem before. Here's what I do if I encounter that. So it's this sort of what we call, there's an experienced engineer, right? He knows what to do and he's learned it over decades. And how do I bring AI in to essentially do the job of that guy? So that is essentially the challenge that we're working on now.
Yeah. Any other places in the design process where AI is getting inserted?
It's pretty much throughout. I mean, you go from start to finish. You essentially start with the specification of the chip, like say architecture optimization, actual implementation of the chip on the physical circuit so that it goes and can be manufactured throughout the process. And everywhere humans are heavily involved, and there's a lot of room for automation with AI. But one of the key things there is you kind of have to bring the human knowledge into the process. It's sort of like if you think about, say, you ask ChatGPT a question, right? And it gives you an answer. The answer comes from all the sources that are out on the internet. They scraped all kinds of information, and it will give you an answer. Usually a pretty decent answer, oftentimes an answer that isn't quite correct because the information wasn't always right. But it was sourced from somewhere. Now, in our domain, that's kind of tough because it's expert knowledge, right? It's sort of like there's the craftsmen that know how to do stuff. And how do I get that information into AI? That's one of the big challenges that we are working on, obviously.
I've done a lot of work with self-driving, not personally, but study in self-driving cars. And, that's an area where they're simulating whole worlds. So I imagine with the EDA and with chip design, there's simulations too. So instead of having to build something and test it and hope it works, is all of that just simulated now by AI?
Yeah, I mean, luckily we have the EDA tools that essentially can simulate things. And therefore, we don't have to go into the real world. When we do, say, our AI development, we don't need to actually build the chip because we have the core tools that can guarantee that the chip that we're trying to create will work once it's produced. So that is an advantage compared to the self-driving cars. I don't actually have to go out there and drive around. The disadvantage, on the other hand, is like if you want to compare with self-driving cars, which is always one of a good comparison because everybody can associate with it. I think there's two things. Number one, I would argue that getting a self-driving car is not as advanced as, say, a human design engineer. Now, I don't want to put down driving. Of course, driving takes time. And like my daughter, for example, is a new driver. And, it takes experience, right? It takes a while to know how to react to certain things. So you have to learn it too. But still, in comparison, I just brake, I steer, I turn the corner, and I have to react to certain situations. There's no doubt. But the advantage, I think, the companies have that built those self-driving cars, whether it's Waymo, Tesla, or Mercedes, they essentially have lots of public data. They can drive around our public streets and they can gather all possible scenarios of what could happen, right? Well, actually, the disadvantage for a human is I may not have experienced those scenarios. Like, luckily, to some degree, I have never been in an accident. But if I get in the situation, how do I react? I don't really know, right? Because I haven't done it before. So that's actually something where self-driving cars would have an advantage because they've seen it all.
Amazing. And now, you guys also just bought a new company, right? So Synopsys bought Ansys, which means you are, in a way, you have been sisters. Now you're coming together. Tell us a little bit about this acquisition, because it really does expand the capabilities and the scope of what you're doing as a company. Tell us about this acquisition and what that means for the world of EDA.
Oh, yeah, very exciting. So thank you for mentioning this. So the Ansys acquisition, I think, has been a big strategic step for us to grow our company. And there's implications on the EDA domain and also implications outside of the EDA domain. There's capabilities that Ansys has that work together with our EDA products for semiconductor, but we also have completely different domains. And it's actually very interesting to talk to those folks. Like, say, we have simulation products from Ansys that design tennis rackets, or they're being used to model the coefficient of cars in a wind tunnel. So instead of running different types of cars through a wind tunnel, you can simulate it. Or like the other day, I was talking to folks and they were talking about designing bottles, like for a bottle manufacturer. So, and you can simulate all these things. You don't actually build prototypes. So that is a huge advancement. And there's also lots of room for AI. And there's actually a domain of what we call physical AI, because we're now getting to the point where the AI that we're producing has an impact on the physical domain because it's actually doing something in the real world. right? While what we're doing is sort of like almost simulated in software. So that's very, very exciting. And it's actually interesting to look into all these other domains that are also connected to the real world, whether it's cars, bottles, or tennis rackets, or nuts and bolts. It's very interesting, the stuff
Yeah, a
that's
tennis
happening there.
racket is definitely a far cry from designing a chip, right? So it opens up the world of design to your company, which I find that fascinating. I think from the chip perspective, I think it's hard for people to imagine how does that impact the world, because it's just a chip in a computer, right? But your customers are seeing breakthroughs in a number of areas because of what Synopsys is doing. Where are you seeing these real world examples of breakthroughs?
Yeah, I mean, you can kind of compare to the heart. Like I would say the chip is the heart of the device, right? And it's not really visible to most people unless you take a hammer and you smash in your phone and you look at it. But it is a very important piece. It's the computational power behind it. And traditionally it was just things like CPU power, but now we have advanced circuits like GPU, neural network things. For example, on your phone, like what you may not realize is you have all these advanced features that recognizes faces. You take a photo, it does the perfect background blur, and it gives you portrait lighting. These things are done through software, but they're actually accelerated through neural processing units in the hardware. So all of these things are not necessarily visible to you, but you use it every day. It's extremely powerful. So that's the beauty of some of this technology.
It's a great analogy, right? Because if you think of it as the heart, every animal has a different heart. You can't take a frog heart and put it in a prince, right? It doesn't work inside of a human. So, and vice versa. So you have a different heart in every device, in everything that actually has a chip in it. I think that's a great analogy, and it makes a huge difference. Obviously, it pumps the blood, the intelligence through whatever device that you're using. So as you think now about, we live in this world of generative AI and AI agents. So AI is expanding beyond what we've known, in terms of simulations and machine learning and that whole world. What impact is agentic and generative AI going to have on chip design and now apparently the design of everything, right?
Yeah, it has a huge impact because, like I said, there's still so many manual steps that a human has to do in the chip design world that is not solved through the traditional software programs. So essentially, the operator of the software that's doing the job for you. Like as an example, from a different world, my wife used to be a graphic designer, and she would design in the 90s. Say she would design logos for companies, right? So she's the expert in how to use Adobe. And nowadays, I think you can just generate most of these things. You just say, hey, create me like 100 different logos for a company or something, and then you pick what you like the best. So these generative capability is very important. And similarly, in our world, the human operator of our so-called EDA CAD tools, essentially, the vision is that human operator is first augmented and ultimately, of course, automated through a system of agents. So many of the decisions where we say, hey, there's the expert's craftsman. He knows how to design a chip. He knows how to run the tools. If all this information is being put into our generative AI systems and then agents operate, they will essentially reason and take actions like an expert engineer. They will look at a problem and it will say, I've seen this before. I know what to do. And the problem is not necessarily exactly the same. It might be similar to a previous problem, and it can actually be compared to a human, be more adaptable because maybe it has seen 10 scenarios or 100 scenarios of similar problems, and then it can try out multiple things and see what works. It's sort of like taking many experts and putting their brains together, and then they have the experience. And actually similar to sort of like the self-driving car. When I said that I've never had to do, say, an emergency maneuver, but if I have a system that has experience or has learned how to deal with all possible scenarios, imagine the power that you have on decision making. And it's the same in the chip design world. you essentially bring the power of the expert user into the systems. And they can automate a lot of these things and make this chip design process more automated, more productive, and much faster.
I did a little bit of research. I saw that you have been speaking, doing a number of keynotes, and you're talking about this agent engineer, which almost sounds like, okay, we're going to reach a point where, not that humans won't be needed, but most of what humans are doing today can be done by an agent, and therefore the ability, and these are your words, these are not my words, moving from having co-pilots to moving to autopilot. Tell us about the future of all this. Where's it going? It's like, I was fascinated by the slide that I saw. I want to hear it from the guy who built the slide and is talking about this vision.
Yeah, totally. And we're not talking about Agent Smith here from the Matrix. We're talking about the good agents that are going to do good things for us. But,
okay, Mr. Andersen, I'm not sure if I believe that.
Well, remember, Mr. Andersen was the good guy in the movie. So anyway, coming back to the agent engineer, yeah, that's essentially the vision that we have set forth and that we're executing upon. And it starts initially, of course, with co-pilots. I think by now everybody's familiar with co-pilots. Like in all kinds of software tools, we have a co-pilot that helps us with certain things. You ask it a question, it gives you a suggestion, but it doesn't actually do anything. So we have, of course, those capabilities developed for all of our tools, and we have co-pilots for our tools. They help make the world better because the human can ask questions. They can say, how can I do this? How can I do that? And the system will say, I suggest you take this action. But the action is still up to the human. So then the agent engineer becomes more like a virtual engineer, where you actually have a system that takes actions. So it doesn't just suggest things, it does things. So I will say, can you please fix these and these things for me? And especially if these are like tedious tasks that I really don't want to do anyway, I'm very glad that I have a system that solves these problems for me. It's sort of like I have an assistant and I give him a bunch of tasks like a virtual engineer. The system does it for me. I still stay in control. I still give it the overall direction. And those agent engineers would sort of work like junior engineers, right? They would know how to fix certain things. They would analyze a problem, reason on what to do, and then take an action and solve it. So that's what we call agent engineer. And that's essentially what we're deploying throughout the process of chip design, from the early specification to the verification, implementation, ultimate manufacturing of the chip. All these tasks can be automated through what we call agent engineers.
Wow, fascinating. Thomas, thank you for sharing your insight on how AI is reshaping EDA and turning this complex human-intensive process into one that's faster, smarter, and more collaborative. For our audience who'd like to learn more about what we discussed, visit www.synopsys.com. That's SYNOPSYS.com. We'll be back next week with another episode. In the meantime, make sure to subscribe to all major podcast platforms and follow the conversation on X and LinkedIn at EM360Tech. For daily insights and content, visit em360.com.